There we go. Now I've got the lights. Perfect. Okay. Welcome to my next presentation. You guys are all here this morning. You already saw me. For those of you who don't know, well, I guess it's in the intro here. My name is Vincent Ledvina. I'm a PhD student at the University of Alaska Fairbanks studying the Aurora. So just started my PhD. In the program, it says I'm credentialed, but I'm technically not credentialed yet. So anything I say, don't hold above my head. Words do not affect or do not represent my employer, all that good stuff. So I'm doing my thesis topic on auroral beads. So if you know what those are, I'm studying those for the next few years. Passionate about citizen science, space weather, risk and resiliency. That's what R&R is, and public outreach. And I grew up in Maplewood, Minnesota. I went to University of North Dakota for my undergrad. If you know the North Dakota dual Aurora camera, that was I helped start that. I'm also an Aurora chaser and photographer, obviously, since we're all here. I think we all are Aurora chasers. And I've been doing it since 16. My first Aurora I ever saw was in 2003, the Halloween storms. And this talk is going to be focused on, answering the question, when will the Aurora be out? And that's a hard question to answer, right? I mean, how do you approach that? So my goal today is to not necessarily explain everything, but give you a lot of the tools necessary to kind of forecast the Aurora, if you can even forecast the Aurora. We're going to be talking about that, is how much forecasting can you really do? So we're going to start out with sort of a space weather 101, very top level, nothing too crazy here, and then just going into the tools and then concluding thoughts. So that's the theme for today. So space weather 101, here are the four main types of space weather. We have coronal holes, we have CMEs, radiation storms, and solar flares. These are the four main types of space weather, and a good working definition of space weather are the conditions around a star like our sun and its interplanetary space, so the solar system, that may affect space and ground-based assets as well as human life. And today, I'm going to be going over three of the four types of space weather. We're not doing radiation storms because they have basically no bearing on Aurora. So solar flares, we all probably know what solar flares are. They're sudden bursts of electromagnetic radiation, usually from sunspots. The light gets here in about 8 minutes. They can trigger CMEs to launch from the sun. They don't cause Aurora directly, so this is huge. Solar flares, if you see a pop-up on your Space Weather Live that there was a X 2.8 solar flare, that does not mean Aurora is coming by itself. There could be a CME associated with that, but a solar flare by itself does not mean there's Aurora coming. Very important. Goes on a logarithmic scale, starting from A class down here all the way up to X. And that means it's logarithmic means that each from A to B is 10 times, from B to C is 10 times. So from A to C is 100 times, from A to M is 1,000 times. So these flares are exponentially larger than the previous class. And really, I start paying attention around the C class to M class level. So the sun's always flaring, quote unquote, at the A and D levels. And long duration flares are almost always associated with CMEs. And what I mean by long duration are these flares that have a big uptick here. That's the flare, but then a really shallow sort of slope coming down. That's called a long duration flare. So if you see that, that's a long duration. Those are almost always associated with CMEs. And I'll get to questions later. I just want to get through the space weather part first. Coronal mass ejections are kind of like sun sneezes. That's what I like to call them. They're basically big clouds of plasma that get burped out from the sun into outer space. And sometimes those clouds are directed at Earth. And when these clouds are directed at Earth, we can determine where they're going with all these different instruments. There's coronagraphs, which you probably may have heard of those. There's models like NLIL. There's sites like the CME scoreboard by NASA CCMC, where you can get all this information that'll tell you where these CMEs are going. And if these CMEs hit Earth, now there's another factor. So a CME gets launched from the sun. We can see it exploding out the sun. That's great. Now we have to know, where is it going? Once it hits Earth, we have to know, okay, is it actually going to cause Aurora? Because some of these CMEs, instead of coupling nicely with Earth's magnetic field and causing auroras, they kind of just fly right on by, don't really care about Earth's magnetic field at all. They kind of just bounce off. So that can happen. So CMEs, that's kind of like the main thing for us down at mid latitudes. We care about CMEs. They give us probably the best Aurora, but they're also really hard to predict, and they're really tricky to model and figure out where they're going to go. No. Okay, so here is the difference between CMEs and solar flares. I guess there's no sound, but basically, this is something I want to drive home, is that a solar flare is just a burst of electromagnetic radiation, which is light. Okay, so a solar flare releases radio waves, microwaves, releases visible light too. You can actually, in very, very strong solar flares, see them happening on the sun. The first observation of a solar flare was Richard Carrington. You probably know the name Carrington. That was a Carrington class event. That was a Carrington event in 1859. That was a white light flare. So he was actually looking at the sun just at a really good time and saw the flare happening through his telescope. It was that powerful. Now, most of the time it's in X-rays or EUV, and we look at the sun with all these pretty filters that give it, the orange and the blue colors and the green. That's all in EUV, extreme ultraviolet wavelength. So that's way shorter than visible light. So we can see these flares are like paparazzi flashes going off on the sun. That reaches us in 8 minutes, so there's no way to predict them. But then these CMEs come after the flare, right after the flare, and they take a lot longer to come off the sun. They're usually traveling around, 500 to 1,000 kilometers a second. Most energetic ones maybe 2,000 kilometers a second, but a flare is at the speed of light. So these CMEs take days to get to us versus flares that take minutes. So just to drive home, this is really important because this is probably the biggest misconception about space weather. Solar flares do not cause aurora. It's just light. And for our purposes, they're pretty much, they don't affect us too much. If you're a ham radio operator, yeah, you probably want to pay attention to solar flares because they're going to get tons of noise on your channels and things like that. Okay. Already did that out. Okay, high-speed streams. So we have CMEs, now we have high-speed streams. High-speed streams come from coronal holes, and no, it's not an actual hole in the sun, although it does look like one. So if you see any news articles from CNN or Fox that say, oh, there's a giant hole in the sun and it's going to cause issues, it's probably a coronal hole. It's harmless. So these high-speed streams are produced by coronal holes, and the physics of it is that there's kind of a cooler region in the sun's atmosphere, which is why it appears darker in the image. And that cooler region is associated with open magnetic field lines, which just allow the solar wind to spew out from the sun really, really quickly. So these coronal holes give us fast solar wind or high-speed solar wind, which is why they're called high-speed streams. Now, when this coronal hole is rotating with the sun and the sun rotates, the solar wind is always coming off from the sun, like a hot cup of coffee. You have the hot cup, which is the sun, and the coffee is sort of like the gas or plasma in the sun. The steam coming off is like the solar wind. It's constantly coming off the sun. These coronal holes rotate and they compress the solar wind in front of it, creating almost like a snowplow, which is up here. You have a compression region, and you can actually see that in the solar wind. And I'll be kind of getting into how to detect coronal holes in the solar wind. But if you look at the density, which is this orange, you can see it ramp up right before the high-speed stream comes in. So if you see a nice gradual ramp up in density, drops off, followed by nice high-speed solar wind, that's a coronal hole. That's a telltale sign. And these coronal holes can last for many days, weeks, sometimes even multiple solar rotations. And if you look at the NOAA 27-day KP forecast and you see, oh, there's a KP5 in 20 days, what is that all about? Well, it's because they're assuming the coronal hole, which you can't actually see it at that point. It's behind the sun from our point of view. They're assuming it's going to survive and then rotate back around. And they just take whatever we saw the last rotation and just plop it 27 days in advance, because that's how long it takes for the sun to rotate. So in case you're wondering, these long-term KP forecasts and like why you see a 5 or a 6 3 weeks out, it's because of these coronal holes. And that's a little, it's kind of like guessing, right? You don't quite know if it's going to last. So I never go off the 27-day, but in case you're wondering where that comes from. So now we're getting to the magnetosphere. So the solar wind, that's what everything propagates through the CMEs, the coronal holes. It goes through interplanetary space out from the sun. Then it has to hit Earth. And what happens at Earth? Well, it's a whole other field. So there's solar physics, there's interplanetary physics, there's magnetospheric physics, then there's ionosphere. So again, this is just a very broad overview. You could spend an entire PhD on this thing right here. So obviously can't get into everything now. But So the magnetosphere basically controls and dictates how the energy from the solar wind gets transferred down into Earth and then into the aurora. So how does it happen? Well, through magnetic reconnection. It's known as the Dungey cycle. Dungey was the last name of the person who found out about this. So obviously that it happens in science all the time. And what happens here is that you have solar wind that comes in, and if it's BZ south pointing down, Earth's magnetic field is pointing north, just naturally. That's just what it is. It's always flowing from the south pole to the north pole. When you have a south and a north that come together, the field lines reconnect and the energy can get transferred. That's why BZ south matters. So in case you're wondering, here's actually the coordinate system here. So it's kind of complex, right? Like magnetic field is actually not just a thing. It's really three quantities. There's an X and a Y and a Z. It's a vector. So you have the Z, which is up and down. You have the Y, which in this case is kind of into and out of the screen. Then the X is pointing to the sun or away from the sun. And all we care about right now is BZ. So if it's oriented south, that means there's more downwards component, which if the Earth is always BZ north, that means more magnetic reconnection. That's why BZ south matters. And also another important thing to note is that the sun's energy doesn't just get funneled directly into our poles. This whole magnetic reconnection business means that there's a day-side reconnecting event, and then the plasma has to get convected or kind of draped behind Earth, and it eventually reconnects in the magnetotail, which is back here. So a lot of artist depictions or models you see of the solar wind interacting with Earth just show the solar wind, directly causing the aurora, but really there's a whole lot more going on. When you see a BZ south, yeah, that's correlated with more aurora, but that's not the whole picture. And that's beyond the scope of this talk, but just realize that there's a lot going on here with the magnetosphere magnetic reconnection. So this is sort of a little video I found that shows magnetic reconnection. So there's not too much of an intro here. Give a nice visual. So yeah, this will show kind of how that works. So there's a nice aurora there. So that's what we all love. Looks like Norway or something. Okay, yeah, so these are satellites. So you can measure magnetic reconnection with satellites, which is kind of cool. I'll be going into that a little bit. I think it's probably MMS. There's no satellite, but I'm sure they're talking over this. Yeah, here we go. So this is kind of neat. So this is actually what the auroral oval looks like from a sort of space perspective. These are all sky cameras. This is the Themis mission. There's a Themis network of all sky cameras. You can actually see the auroral oval is not just a blob, it's more structured and it's really dynamic. So yeah, you have charged particles gyrating along magnetic field lines, so that it's going into a bit of the physics there. Here we go. So you have this magnetic reconnection event that will take place, I hope at some point here. Yeah, so in the tail, so this is assuming that the field lines have already draped over. That magnetic reconnection in the tail is actually what triggers the aurora. So you have to have reconnection on the day side. That's with the BZ south. The field lines kind of get draped over, then they eventually have to close again in the back. And all the particles are trapped on these magnetic field lines. It's like you have a rubber band and you're stretching it, and there's like a bunch of sand on the rubber band. You know how you actually drop it in the sand pit or something and it gets all this stuff on it. So imagine you're stretching that and you kind of let go, all the particles just get slingshotted off. So yeah, that's really oversimplified, but now moving down into the ionosphere. So the magnetosphere is in outer space. The ionosphere, now we're starting to get down to the ground. We're in Earth's atmosphere at this point. So this is a layer in the atmosphere way above the clouds. This is why clouds, terrestrial weather matters along with space weather. It's because the aurora takes place way up in the atmosphere, 60 to 300 miles in altitude. So this is where the aurora is actually created. It's created by chemical reactions. So you have charged particles from the magnetosphere coming in, interacting with gases in our atmosphere, and there's chemical reactions that take place which produce light, and that's the aurora. So it's known as ionization. That's the sciencey term, and the color is determined by the gas being impacted. This is the aurora on a global scale. So just to kind of zoom out now, all this is happening on the scale of the entire Earth. So the aurora is happening at some point around the world at all times. The auroral ovals are probably what we're all familiar with. It's sort of this oval-like structure. It forms around 68 degrees geomagnetic latitude. So if you're in Fairbanks, that's right overhead for you. If you're in Churchill, you're in northern Iceland, you're in Tromsø. That's where the auroral oval sort of rests. That's like its resting place. So the auroral oval, if you travel to that area of the world, you'll see aurora in some form every single night that it's clear. The ovals expand equatorward, so the northern lights come down south, the southern lights come up north. During geomagnetic storms, and also over the course of an entire night, from your perspective on the ground, the auroral oval rotates from the east and then rotates out through the west. So actually, what a lot of people don't know is that even on really weak nights, you could probably get some glow from here in Wisconsin, from up north in Minnesota, just by waiting long enough for the auroral oval to kind of swing through. And the best time for that's around magnetic midnight, which is dependent on your location on Earth, your time zone, your geomagnetic latitude. But for here, it's actually nice. It's right around midnight locally. So if you just wait from like 11 p.m. to 12 a.m., 1 a.m., you have a pretty good chance of seeing something. And over the course of a night, the aurora just generally gets stronger. So there's that factor too. Now there's substorms. So you have geomagnetic storms, which push the auroral oval further south. You have the auroral oval rotating, so it gets better over the course of the night. Then you have these substorms, which are like individual little events throughout the night, usually 1 or 2 a night, which cause the auroral oval to just go crazy. And there's aurora that becomes really like filamentized and goes running from north to south. That's when you get the dances, okay? So if I go back to show the video, that's a substorm right there. So when the aurora explodes, you're seeing a substorm. And these happen roughly 1 to 2 times a day or once a night, and usually right before magnetic midnight. So MLAT or MLT is magnetic local time. That's the abbreviation there. There we go. Okay, here are the colors of the aurora, just in case you're wondering. So the pink on the bottom is diatomic nitrogen, and then the green and the red are oxygen. I'll let you guys look at that. Also, these slides, I should note, I'm recording, and these slides will be made available. So, there's a lot of references to resources in here that I have. I'll be linking all that in the presentation, which then when you open it up, this is all Google Slides. So when you open it up, you can just control click or command click, it'll bring you right to the site. So don't worry about getting a picture of everything, because it'll all be made available later. But yeah, so here are the different colors, very classic, pink on the bottom. You see that with the highest energy auroras when it's dancing, you kind of see like that pink fringe. That's what this is, it's nitrogen. And then the green and the red are just oxygen. So can we predict space weather events that may cause aurora? The answer is somewhat, kind of. It's, there's a lot of interpretation that goes into this. So coronal mass ejections, as I said, usually take around 1 to 4 days. We can predict the arrival time within about 10 hours now, 7 and 10 hours. So the stronger the CME and the more Earth directed it is, the easier it is to predict. If it's sort of a faint eruption and sort of off to the side, yeah, maybe not so much. But we can't really predict the geoeffectiveness. So if you were in Christian's talk earlier, he was talking about the flux ropes. That's one way you can sort of look at a CME and coming in and say, okay, well, it has this orientation, so we should expect this level of BZ, this level of BY for the next 12 to 24 hours. But still, it's really hard. High-speed streams are a lot easier to predict because you can see them coming. The onset is much more gradual. It takes multiple days for them to sort of ramp up. And you can also see them on the sun rotating in. So you have about a 1 week heads up when you first see them rotating in from the western or from the eastern limb. And then the geoeffectiveness, also depends on many factors, because it's usually not such a strong storm. It's usually pretty wild with the BZ. It gets really, choppy, but they're a lot easier to predict. Okay, yeah. So this is a common model called the NLIL model, WSA NLIL model. We've probably all seen this, but it's used by NASA and NOAA to model CMEs as they expand out into the solar system. We predict the strength of the aurora now. Okay, so we have the space weather aspect down, kind of. Once the space weather gets to Earth, can we predict what the aurora is going to do? The answer is pretty much no. As much as you want to say, oh yeah, I know what it's going to do. To be honest, like there's so much more going on than just solar wind or just KP. There's a lot of factors, and different types of aurora are caused by different phenomena. So like, for example, diffuse aurora is a completely different phenomenon than discrete arcs or pillars or steam. And those are all affected by different factors in the solar wind. So you have all these things going on at once. To be honest, it's really not worth, getting into aurora prediction beyond like 15 to 30 minutes or maybe a couple hours. There's really no way to say, oh, we have a CME coming Sunday night. and I expect there to be really, really good aurora because you honestly have no idea, right? It could even be cloudy, right? Like the clouds are going to completely cancel that out. So KP, so I'm going to be going over all these different data sources here. So solar wind, the lead time is usually 30 to 60 minutes. So the satellites are upstream. Upstream just basically means closer to the sun of Earth. They're at this like Lagrange point where they basically stay put. There's no gravity there essentially, so it just kind of floats there. So when you see the solar wind hit ACE or Discover in your Space Weather Live app, you have about an hour before it actually reaches Earth. And then once it reaches Earth, it still has to go through all that magnetic reconnection. So that might take another 20 to 30 minutes. So you kind of have a heads up there. Ovation Prime is based on solar wind, so that's the same thing. Knowing the CME flux trope structure can give you better predictions, right? Christian was going over that. You also have the GOES magnetometers, which kind of gives you some context. I'll be touching on that a little bit. KP is kind of useless. AE index or other ground magnetometers are really nice. They are almost real time, so they give you sort of a good picture of what's going on now. And then ground truth visuals like Michigan Aurora chasers, other webcams, Aurora source, that's the best, right? You know exactly what's going on. Who cares what the solar wind's doing? If I see Aurora on the North Dakota cam and I'm in Grand Forks, okay, yeah, it's happening like in my backyard, I should probably go out. That's the best. So if you can find a good list of webcams, just bookmark all those and keep them up on your TV all night. That's honestly the best way to do it. People do that. So yeah, here's what we're going to go into. I'm going to touch on these all briefly, but if you have questions about specific sources, just feel free to come to me after the talk because I've used everything here. But we're going to go into different ways to track space weather, and then we're going to go over different ways to track aurora. So there's all these, probably you've heard of a lot of them, but maybe you haven't heard of SEEDS or Solar Demon. Probably heard of a lot of these, but maybe you haven't heard of the GOES magnetometers or HP 30 or 60. So stay tuned. So why do we track space weather? Well, it's important to know what's coming. Some people would say, who cares? All I care about is L1 and what hits ACE and Discover and the Space Weather Live app, which, yeah, that's fair. But if you're at mid latitudes like we are here and you want to plan for, a big CME coming, you want to plan to see auroras and you want to go drive somewhere, then you want to know, okay, well, what should I expect in the next 1 to 3 days? What should I take off work? Or where should I book my hotel? Or, how much should I budget for gas, wherever I'm going, right? So that's why. And then how? Well, we can monitor the sun directly, and then we can use models to determine where that activity is going in the solar system and whether or not it's going to hit Earth. So let's talk about CMEs. So the first way to tell if a CME is going to come off the sun is looking for a big solar flare. Now, CMEs don't need to happen with solar flares. They can come from other ways too, but this is probably, the most common thing is to see a solar flare, big solar flare, CME comes off right after that. You can look for what are called EUV waves in Solar Demon. So, I'm not going to get into the whole weeds of this, but this is what Solar Demon looks like. Again, these links will be on the presentation. But basically, this takes your normal sun image and applies a filter to it so you can see the blast waves a lot better. And you can see these blast waves coming off, and then okay, there was an explosion. After that, was a CME actually launched? Because sometimes these explosions are kind of confined to the surface. They don't actually make it off the sun. You can look at these things called coronagraphs, and you see like this big halo-looking thing. That's a CME coming right at the spacecraft. So a coronagraph is like an artificial eclipse. In case you're not aware, there's an occulting arm, which they filtered up really nicely here, but usually it's like right here. And then there's an artificial eclipse being created around the sun, because this is taking an image of the solar wind basically around the sun. And the sun's really bright, right? So it's trying to block out the brightness of the sun. Then it's able to see all the faint stuff that's coming out, all these CMEs. So it's looking right at the sun. So if you see something coming at you, that's going to form a halo around the coronagraph. So that's why full halos are associated with Earth-directed CMEs. And I'm not going to go into how to read coronagraphs because it's more complicated than that. In fact, it's way more complicated than that. But if you see a halo like this, 99% of the time, you're going to get something on Earth. So, okay, I'm not going to go with this just for the sake of time, but this is Solar Demon showing a really nice blast wave here. So, I mean, if anything, they're just pretty pictures to look at. Like, I always like going on the site and just checking out what was going on. And then on the right here is a coronagraph showing a big CME. So here's another really good site. It's called, it's the CCMC Coordinated Community Modeling Center out of NASA Goddard. They do what's called a CME scoreboard. So this gets updated as soon as the CME lifts off the sun. So if you don't want to mess around with coronagraphs and looking at things, CCMC is monitoring, right? They have a whole space weather office at NASA that's designed for the Artemis program. So I mean, there's 24/7 people looking at these things. If you don't want to be if you don't want to spend hours and hours getting into the weeds of coronagraphs, just look at CCMC, look at the CME scoreboard. When you see an entry for a new CME, so this is the data here of the CME. So this tells you when it's actually happening. So if you see a big solar flare, right? Space Weather Live, oh, there was a X8.5. Holy crap, that's a big one. Check CCMC scoreboard in a few hours and you'll probably see an entry. Click detail and you get this right there. You just click on the link, it gives you a GIF of the Enlil model. You can even get like KP predictions, although I would take those with a grain of salt. But you get an Enlil model and boom, you're good to go. So yeah, this is a semi-recent one. We actually have a bigger CME on the way. You've probably all heard, but this was a recent run. So yeah, if you want a really easy way of seeing what's going on, I mean, there you go. It really takes the interpretation out of it, right? Why not just trust the scientists? I mean, they know what they're doing. So how to actually detect an impact at L1. Again, this is really, really broad, but basically just look for a spike in speed, density, magnetic field. That means a big shock wave has just hit the satellite and everything's going nuts. Also, you can use this tool here. It's called ACE EPAM. So it stands for electron, proton, and alpha monitor. And essentially how this works, just really basic physics here, is you have these really light particles that kind of get accelerated ahead of the CME. So as the CME approaches Earth, these really small particles, you'll start to see them. You'll start to see the flux of those particles or the number of particles hitting the satellite increase. Then suddenly you get this really big ramp up, which is the CME approaching. So you're like, holy crap, the CME is probably coming. You see it sort of plateau, and then you see the arrival of the CME. And then at this case, at this point, you would see this too. So the only problem with using ACE EPAM is that the CME is really wide, and that radius of those small particles also extends beyond the CME in the other directions too. So you might see this, and it just kind of trickles down. So that means the CME was close to you, but it never actually hit you. So this is for, I'd say, like the advanced user. But otherwise, Space Weather Live, NOAA, they give you alerts when these they're called sudden impulses, these shocks are detected. So, if you're looking in the solar wind, you see this big spike, that's a CME impacting. Using solar wind data, this is also really broad, but self BZ is generally good. It's kind of like an on-off switch for the Aurora. Steady self BZ with a short 15 to 30 minute north BZ flip can actually trigger substorms. So this is something that a lot of people don't realize, is that a really sustained self or field seems great, but actually you kind of want it to jump north for a little bit and then head back down, because that sort of shocks the system, if you will, into giving you more aurora. High BT is good. I kind of call it as like the leash. So if the BT is really high, but the BZ is kind of around zero, well, the BT could get really, really low, because it's all just an equation, right? The BT controls how much BZ you have or could have. So the BZ, for example, will never be lower or a higher magnitude than the BT. So it's kind of like a leash. So if you see a huge CME coming in, it's like, oh, we have a BT of 30 nanotesla, that's huge. If our BZ is really small, well, it could get really negative. It could go down to -30. It's just not there yet. So it's just good to keep in mind that. Also, the Ovation Prime model, this is all solar wind. So people think it's actually the Aurora. No, it's just a model. So, and we saw earlier, the Auroral oval doesn't actually look like a donut. It's way more structured than that. So again, this is a good resource, but keep that in mind. It's not going to show you substorms, for example. It's not going to show you Steve. It's not going to show you like Aurora being seen down in California that you can see on the horizon. It's a little low. It shows you the probability of overhead aurora. So if you're not in the red, you're okay. You can probably still see it. If you're not in this little green cutoff, it's not like the aurora magically disappears right after this. You'll probably see it down here too. So just keep that in mind when you're dealing with ovation. Not going to really get into this too much, but here's what solar wind, here's what all the numbers mean. The white is BT, higher is better. Red is BZ, lower is better. The blue, we're just not even going to talk about. That's phi angle. The Orange is density. That's how many, basically the particles per second. The speed and the density both control what's called dynamic pressure of the solar wind. So the higher those numbers, the better generally. And the green is temperature. So actually what's kind of cool, this is just like a sidebar, but if you're looking at a CME versus a high-speed stream, if you notice the temperature in high-speed streams is actually usually higher, much higher than the background solar wind. Temperature inside of a CME core is usually really, really low. One thing to note about reading these plots, you'll see this in Space Weather Live. I'm guessing a lot of you use Space Weather Live, so I'm just going to keep saying that. But you see all these like weird like fluctuations here. It looks like these are shocks. Actually, if you look down here, you see, people sometimes miss this, but there's these little yellow marks here. And if you read, there's suspect and error. So this instrument on board Discover is really not good. The density and speed, it's bad, right? We've known this for a while. So the plasma measurements, which are temperature, speed, and density, are spurious. They got a lot of spurious readings. So keep that in mind, right? Don't get excited if you just see a huge density flip because it might go back down. Like sometimes you'll see densities at like 150. It's like, there's no way. And then in 15 minutes, it goes back down to 10. You're like, okay, that was a glitch. So ACE doesn't have as many issues, but it's aging. So over time, it's going to get worse. But what's good is that the magnetic field measurements are completely fine. So the only things affected are these three. Just thought I'd point that out.
Are we gonna get a new one?
Yeah. So I think, yeah, there's a lot. It's actually nice. We haven't had a space weather satellite being flown in a while, but there's a bunch coming. So SWIFO L1 is the new space weather follow-on. L1 is a NOAA mission. I think that's launching in 2027. So that'll have a new L1 monitor. So, okay, high-speed streams, already mentioned this. I have a lot of slides, so that's why I'm kind of rushing here. But again, feel free to come after me after this. You'll see a density ramp up followed by speed. And that's kind of indicative of that snowplow effect of the high speed pushing the slower solar wind ahead of it. It's like, come on, guys, get going. So you see this density ramp up, and then after it kind of ramps back down, you see the high speed behind that. And you'll see, here's the temperature increase too, as I was talking about. You see it starts out pretty low and it gets a factor of 10 higher. Yeah, so other notes. Yeah, so when the coronal hole is at center disk, so here's the disk of the sun, when it's in the center, just because of how fast the sun rotates, that high speed solar wind's about 3 days away. But you'll also see that in the 3-day NOAA forecasts and all that stuff. So in case you're wondering, you have about 3 days if the leading edge of the coronal hole is at center disk. And here's just some canonical solar wind, what we should expect there. And here's a very textbook high-speed stream. In previous solar cycles, these high-speed streams would actually drive shocks. Like that's more physics, but we're not seeing that in the solar cycle. So you should see a pretty gradual ramp up in the speed and the density. But if you have a really, really fast coronal hole, really powerful coronal hole, you can actually get shocks. So it might look like a CME, which is kind of confusing. Yeah, so sometimes can drive shocks. Okay, here we go, tracking the Aurora. So now we're done with space weather. We know where the space weather is going. How about the Aurora? Well, as you can see, there's a lot of stuff going on. There's a lot of different plots. We have GOES magnetometer, we have KP, we have AE, we have HP, we have all sky cameras, which actually this is cool. This was a satellite, I think, outgassing or something. This is the poker flat all sky camera. But yeah, we have all these different indices. So what are they? How do they work? And which ones are useful? Well, KP is not, it's really not that useful. So hopefully, if you're going to take anything away from this, solar flares, CMEs are different. Ovation is just a model. KP is pretty much useless. So what is KP? Well, it's a 3-hour average of past geomagnetic activity, global geomagnetic activity. And the stations are not even high latitude. So if it's a magnetometer. So if you're looking at a magnetometer, you really want underneath the Aurora, because then it can pick up all the fluctuations from the Aurora. But these magnetometers are more low latitude. Like there's some that are in Japan and like lower Europe and South Africa. There's no Aurora down there. So why would you use data from those places? Plus, it's a 3-hour average. So here's a really cool plot. This is a magnetometer, one of the stations that's used by KP. You can see how much it's fluctuating, right? Like this right here might be a little substorm. This is probably a big substorm. This might be a substorm here, but this is what KP does, just smooths it out. So you're losing all that data in this smoothing, in this averaging. So just basically never use it. And here's the same thing here. You can see the differences between all these magnets. These are all the stations here, right? So KP is actually an average of all these stations. And here they all are. Here's what they all look like. KP broken down for you right here. And this is what you actually get. You just get these little bars. I mean, it really cancels out what's actually going on. So why is it used then? Well, because the data goes back for decades. These magnetometers have been around forever. So when you're looking at scientific studies, which are what the community uses to validate models, to make models, to determine different parameters of the atmosphere, KP is used all the time. So that's why NOAA uses it, because NOAA forecasts for customers like airlines, power grids, satellite operators. They just want to know, okay, it's a KP7, what should I do? It's a KP5, what should I do? They're not chasing the Aurora, so they don't care what the Aurora is really doing, why KP is not so great for Aurora. So NOAA uses KP, but that doesn't mean that you have to use KP. And it is useful in hindsight, to know how strong an event was. Like a KP9 is obviously stronger than a KP1, for example, but beyond that, it's really not that useful. HP 30 and 60 are KP, but on a finer time resolution. So HP 30 is 30 minutes, HP 60 is 60 minutes. And actually, once you get down to 30-minute resolution, it's actually not that bad. Like you can use HP 30 if you just want a number 1 to 9. Actually, HP 30 goes beyond the 9. It's actually extended all the way up. In the 2003 storm, technically the KP, if it were a 30-minute bar instead of 3 hours, would have been an 11. So if you're, it was actually a KP 11, that 2003 storm. Anyways, you can see just the differences here. So KP's in the blue, HP 30 and 60, I think, are in the HP 60 looks like orange, HP 30 is green. So you can see it captures more of the dips and the peaks and the valleys and things like that. But still, it's a global measure of geomagnetic activity, and it's still average. So, I mean, it's better, and it can give you those intense bursts and maybe pick out the substorms, but it's still not great. DST, just thought I'd mention here, I rarely use this. It's more of a real-time measurement, but the stations, you can see the stations here, they're all low latitude, and there's only a handful. There's actually one, so there's 40, that's it. So this is a very historical measurement. This goes back hundreds of years. So this is used just because it's historical for the most part. And it's a measure of the ring current, which is around Earth. So in case you're wondering why it's negative, when you have these particles spinning around Earth, because of Faraday's law, it induces a magnetic field that opposes Earth's own magnetic field, which is why you get a decrease. So this is actually a measure of Earth's magnetic field, and it decreases during a geomagnetic storm because all these particles are getting accelerated and creating its own magnetic field, which opposes. But anyways, I thought that was interesting when I first learned about it. So good for characterizing the overall strength of a geomagnetic storm, but not really great for auroras. Plus, I mean, even if it was, you're still dealing with all low latitudes anyways. So Auroral electrojet index, this is where things get interesting. So this is where things get good, right? So now we're talking about a chain of magnetometers. It's still averaging, right? So you're not getting like exactly what's happening in North Dakota or exactly what's happening in Alaska, but at least you're covering the Aurora now. So when we're looking at these magnetometers, it's important to know where they are and how close they are to the Auroral oval. So these are right in the Auroral oval. And this is a really nice, if you just want a number, right? That's what a lot of people want, is just at what number should I go out? If you just want a number, usually 500 to 1,000 nanotesla, and the AE is a good time to go out Aurora chasing. There's usually enough activity in the electrojet where you can see auroras at mid latitudes. So it's still an average of magnetometers, but it's basically real time. So here's what the plot looks like. This was for September 3rd, and you can see it captures all the little wiggles really well. So 500 is here, 1,000 is up here, 1,500 is here. Just for some context, like the 2003 storm was actually off the charts. It was like 2,500. November 4th, 2021. I think we all remember that 2 years ago. That was around 1,500 to 2,000. So big geomagnetic storms are going to cause big fluctuations in the AE, but it's nice to know what's going on, because sometimes if you don't see Aurora, but the KP is really high, if you check the AE, it might be down at 0. And you're like, okay, well, that's why. So KP just smooths everything out way too much.
Is that historical? Like, can you go back?
Yeah.
And look?
Yeah.
Like
So
go back and look at
so the Aurora electrojet index has been around for 30 or 40 years. So you can go back pretty far.
The electrojet is.
The electrojet is so the Aurora is an oval, and the electrojet is within the Auroral. So it's a sort of current of particle, or it's all these particles forming a current, which you can measure then. So magnetometers measure currents in the ionosphere. They induce a magnetic field in the ground, which then you can measure with the magnetometer. So the auroral electrojet is the current that's produced by the auroral. And yeah, so great for capturing substorms too. Although substorms are still localized, but they are, so they start out at a certain point and then they expand to reach the entire globe. So the actual initiation of the substorm might not get captured in the AE, but you'll see it if there's a huge spike, right? Now this is cool. So the GOES magnetometers, this one is like pretty niche, okay? But it's really powerful. Now these satellites were not designed for space weather. They're designed for just terrestrial weather, like taking images of clouds and stuff. But they have some magnetometers on board. There's a GOES East and a GOES West, and they're geostationary. So the West is basically right over Washington, USA. The East is sort of over Maine-ish. The exact longitudes are on the website, but so they're geostationary, which means they're always over those places. So as Earth rotates into the magnetotail, you can see what's going on in the tail, which is really cool. So it's rotating into the area which causes aurora, as we saw with that magnetic reconnection, right? It's all the stuff from the night side of Earth that's streaming in and hitting our atmosphere. So I have a thing on I have a whole blog post on my website that goes into it, but essentially you get these plots here. So if you go to the website, the blue is the West satellite and the red is the East satellite. As it goes into the magnetotail, so without any activity, this would just be a pure sine wave. It just go like this. But all these little bumps are caused by injections of particles from the tail to Earth's night side, which can cause aurora. And when you get these really big spikes, those are big injections, those are the substorms. So you can actually see a substorm happening in real time with this plot. You literally see it happening. Once you see this thing turn up and start shooting up, you look up and there's aurora forming. It is that good. And I use this all the time in Alaska, even though I'm more west of the satellite. I use this all the time, and it's great. And the more down it is, basically, the more charged up the aurora is. The more it shoots up, the more particles get released. So you can use this for so many things. It's really cool, and I don't think it's talked about enough because it is a U.S.-centric tool, right? The satellites are over the U.S. So if you're in Iceland, this isn't going to work. If you're in Norway, this is not going to work. These satellites are stationed over the US. So they're biased towards us, which is okay, but we have the best stuff. But yeah, so definitely take a look at this. The physics are beyond the scope of this talk, but it's really, really neat. So now magnetometers, there's regional/local magnetometers you can probably find data for. This is almost the best in terms of looking at what the aurora is doing. And basically here, without going into the physics of it, the larger the wiggles, the more activity there is and the better the aurora is going to be. The challenge is finding a magnetometer that's close to you. So that's always been hard for me, is what magnetometer is closest to Minnesota? Is it the one in Kenowa? Is it the one in Brandon? Is it the one in Boulder, Colorado? Probably not that one. But yeah, you get a lot of data with these. This is just an example of all these different data sets overlaid. So this is for Alaska, but you can see in the magnetometers when you have this really strong dip is when you get the substorm. So basically when you see these dips, really strong dips, that's when the substorms happen. And this is nice because sometimes substorms form right over you. So you really only care about your station. You don't care about the global response. You only care about what's going on right where you are. So you'll see that in your own local magnetometer. So they're measured in XYZ or HDZ components. Again, kind of beyond the scope of this, but basically the more it goes down, the better the aurora is going to be. And you can see here with the GOES satellite, it happens. This is what I was just showing on the previous slide. Yeah, you see on this slide, this is the same plot here. It's just in a different scaling. It's the same data, but it correlates 1-to-1. So just going to show you how good this satellite is versus a local mag. It's almost the same. So yeah, I'll probably post something like a blog on my website about it because there's some good magnetometers close to us. Canada has a really good network of magnetometers. So does the US, but they're more lower latitude. But yeah, so you can use local magnetometers as well, but really does a good job. So ground truth data is probably the best though. I mean, you can get really obsessed with looking at the data, which you know, I'm definitely obsessed with it, I'm not gonna lie. But at the end of the day, if you just join one of these Facebook groups and just turn on your notifications, when there's a geomagnetic storm, and people are gonna be out looking for Aurora, right? There's also dedicated projects like Aurora Source, which users can submit reports that get added to the Auroral oval map. You can see where the Aurora is actually taking place. And then you can use webcams, social media, Aurora Source. These are the best tools and they don't lie, right? Sometimes the data, you see the solar wind do one thing and you're like, well, the Aurora wasn't supposed to do that. I saw the VZ go south and the Aurora disappeared. Well, the VZ went north, but I saw you know what I mean? They can get really complicated. So just looking at a webcam like this, I mean, if you see this going on, who cares what the solar wind's doing? It's time to go out. So everything else are proxies, but ground truth is 1-to-1.
It's about 5.
Yeah.
4.
I'm pretty much done. So, apps, Space Weather Live is pretty much what you should be getting at. All the rest kind of give you like a % chance, which is just based on ovation. Sometimes they try and do their own tricks. Don't trust that. Like, you know, most of the times they're not scientists. They don't really know what they're doing. They're just trying to make something visually appealing. And if you're paying for an app, you're paying for something that's not worth it, in my opinion. So Space Weather Live is the best one. And yeah, concluding thoughts, just gonna really wrap up here quickly. It's hard to track the Aurora, to be completely honest. So, you know, if you're gonna take away anything, if you're not confident in tracking the Aurora, it's not because you don't know enough, it's because it's really hard. And there's a lot of data out there to go through. And the best is looking at ground truth data like Facebook groups and social media. CMEs and high-speed streams are what we have to watch for. Down here at mid-latitudes are what give us the big shows. Best way to track space weather, CCNC scoreboard, ENLO models, best way to track Aurora, AE index, GOES, ground truth data, avoid the KP. And you really need at least a full day or maybe a week or a whole PhD to explain this all in depth. And I'll be putting this slide deck on, I think, the Aurora Summit site somewhere, and then my own personal website too, which is theauroraguide.com. And that's it. Thanks. Good.
Okay, just in a few minutes, they're gonna come out and start moving the walls down. And so if a couple of guys could just hang out for a minute and rearrange the room, that'd be very helpful.
Huh?
And then about probably
No.
10-15 minutes, we'll be ready to.
Why is it?
to
Is there something here?